Common Language Runtime, CLR, is the core component of the .NET framework. It acts as the execution engine that manages and runs .NET applications. When a developer writes code using languages such as C#, VB.NET, or F#, that code does not directly communicate with the operating system or hardware. Instead, the code runs inside a controlled environment provided by the CLR. This runtime environment ensures security, memory safety, performance optimization, and reliable execution. Understanding how CLR works internally is extremely important for .NET developers because it explains how applications behave behind the scenes. At a basic level, CLR sits between the application and the operating system. It controls how code is loaded, executed, optimized, and terminated. The developer focuses on writing business logic, while the CLR handles low-level tasks such as memory allocation, thread management, exception handling, and security. This separation is the reason .NET applications are more stable and easier to maintain compared to unmanaged applications. Before execution begins, the source code written by the developer must go through several stages. The first stage is compilation. When C# code is compiled, it is not converted directly into machine code. Instead, it is converted into intermediate language, commonly known as IL or MSIL. This IL is a CPU-independent instruction set. Along with IL, the compiler also generates metadata that describes the structure of the program, such as classes, methods, properties, and references. This IL code and metadata are packaged together inside an assembly. An assembly can be either an executable file or a dynamic link library. Each assembly also contains a manifest that stores important information such as assembly name, version number, culture, and referenced assemblies. The assembly becomes the fundamental deployment unit in .NET, helping to solve versioning issues and dependency conflicts. One of the most powerful features of the CLR is language independence. This is achieved using the Common Type System, CTS. CTS defines a standard set of data types and rules that all .NET languages must follow. Because of CTS, an integer in C# and an integer in VB.NET are treated identically by the runtime. This allows objects created in one language to be used seamlessly in another language, making true multi-language interoperability possible. Closely related to CTS is the Common Language Specification, CLS. CLS is a subset of CTS that defines a set of rules all .NET languages agree upon. While languages may have advanced or unique features, only CLS-compliant features are guaranteed to work across all languages. This ensures that public APIs remain usable regardless of the language used by the consumer. When a .NET application is launched, execution does not immediately start from the main method. The operating system first loads the application and recognizes it as a managed assembly. Control is then passed to the CLR. The CLR initializes itself, creates the required runtime environment, and prepares the application for execution. This includes setting up memory structures, loading required assemblies, and creating an application domain. Application domains provide isolation within a process. They allow multiple applications to run within the same process without interfering with each other. Each application domain has its own configuration, security boundaries, and loaded assemblies. This improves safety and stability, especially in large systems. Once assemblies are loaded, the CLR performs verification of IL code. This step ensures that the code is type-safe and does not attempt illegal operations such as accessing memory outside its boundaries. This verification process is a major reason why managed applications are more secure and less prone to system-level crashes. After verification, the execution process moves to one of the most important components of CLR, the just-in-time compiler, commonly called JIT. The JIT compiler converts IL code into native machine code that can be executed by the CPU. This conversion does not happen all at once. Instead, JIT works method by method. When a method is called for the first time, the CLR checks whether native code for that method already exists. If not, the JIT compiler compiles the IL instructions of that method into native code. Once compiled, the native code is stored in memory and reused for subsequent calls. This improves performance because the method does not need to be compiled again. This approach also ensures that only the code that is actually executed is compiled, reducing startup time and memory usage. Modern .NET uses advanced JIT techniques such as tiered compilation. In tiered compilation, methods are initially compiled quickly with minimal optimization. If a method is called frequently, the runtime recompiles it later with more aggressive optimizations. This balances startup performance with long-term execution efficiency. Memory management is another critical responsibility of the CLR. When objects are created using the new keyword, memory is allocated from the managed heap. Unlike unmanaged environments, developers do not manually free memory. Instead, CLR uses a garbage collector, GC, to manage object lifetime automatically. The garbage collector works by identifying objects that are no longer reachable from application code. If an object cannot be accessed by any running thread, it becomes eligible for collection. The GC then frees that memory and makes it available for future allocations. This automatic memory management significantly reduces memory leaks and pointer-related errors. The GC uses a generational approach to improve efficiency. Objects are grouped into Generation 0, Generation 1, and Generation 2. Newly created objects are placed in Generation 0. If they survive garbage collection, they are promoted to higher generations. Most objects are short-lived, so frequent collections occur in Generation 0, while Generation 2 collections happen less often. This strategy greatly improves application performance. In addition to memory cleanup, the garbage collector also performs heap compaction. This process rearranges objects in memory to reduce fragmentation. Compaction improves memory locality and increases CPU cache efficiency, resulting in better runtime performance. CLR also manages stack and heap memory separately. The stack is used for method calls, parameters, and local variables. It follows a last-in first-out structure and is cleaned automatically when methods return. The heap is used for reference types such as class objects and arrays. Understanding the difference between stack and heap helps developers write more efficient code and avoid unnecessary object allocations. Exception handling in .NET is fully managed by the CLR. When an exception occurs, the runtime searches for a matching catch block in the call stack. If none is found, the application is terminated gracefully. CLR ensures that exceptions do not corrupt memory or crash the operating system. This structured exception handling improves application reliability and debugging. Thread management is another important feature provided by the CLR. The runtime supports both foreground and background threads. It also maintains a thread pool that reuses threads for asynchronous and parallel operations. This reduces overhead and improves scalability. Modern asynchronous programming using async and await relies heavily on CLR thread scheduling and task management. Security is enforced by the CLR through multiple layers. During code loading and execution, CLR ensures type safety and prevents illegal memory access. Earlier versions of .NET used code access security, while modern .NET relies more on operating system-level security. Still, CLR plays a vital role in maintaining execution boundaries and preventing unsafe behavior. Reflection is another powerful feature enabled by metadata and CLR services. Reflection allows programs to inspect types, methods, and attributes at runtime. This capability is widely used in frameworks, dependency injection containers, and serialization libraries. Without CLR metadata management, such dynamic behavior would not be possible. The complete internal execution flow of a .NET application can be summarized clearly. First, the developer writes source code. The compiler converts it into IL and metadata and packages them into an assembly. When the application starts, the operating system loads the assembly and hands control to the CLR. CLR initializes the runtime, loads required assemblies, verifies IL, and sets up execution environments. When a method is invoked, the JIT compiler converts IL into native code. The CPU executes that native code while CLR continuously manages memory, threads, exceptions, and security. When the application ends, CLR releases resources and shuts down safely. The importance of CLR cannot be overstated. It provides a consistent execution environment across platforms, supports multiple programming languages, improves application safety, and delivers optimized performance. Without CLR, .NET would simply be a collection of libraries. CLR is what transforms .NET into a powerful runtime platform. For developers, understanding CLR internals helps in writing optimized code, diagnosing performance problems, and performing confidently in technical interviews. Concepts such as garbage collection, JIT compilation, memory management, and execution flow become much clearer once the role of CLR is understood deeply. In conclusion, the Common Language Runtime is the backbone of the .NET ecosystem. It manages every stage of application execution, from compilation to termination. It ensures that code runs securely, efficiently, and reliably. By handling complex system-level responsibilities, CLR allows developers to focus on building scalable and maintainable software solutions. A strong understanding of CLR architecture provides a solid foundation for mastering .NET development.